All right. Well, thank you so much, Stephanie and Carlos. We are really happy to be here today to represent OpenROAD, and we too are extremely grateful to your organization as well as the GSOC platform to help us reach out to the larger community in the open source, especially in the area of VLSI or chip design related software projects. And I'll just have a start with a very quick overview of what we are going to be presenting today. So I have with me from our team, we have Vitor Bandeira, and he's based out of Brazil, but he is a key member of the OpenROAD team. And he is going to be, I'm going to be first of all walking you through the just what the OpenROAD project is about, and hoping to give you a broader overview and appreciation of why we are doing this an open source project for chip design. And then Vitor, who is going to kind of take you a little bit more deeper into the project, how it's organized on GitHub, and how things are set up for our user community, for our developers, how the project works, and kind of dig a little bit into the innards to give you a sense of how this happens. And then we are very happy to also have Ethan Mahintorabi. Ethan is from Google, and works very closely with the OpenROAD team. And I do want to mention that Google is a major sponsor of this project, and they are, in fact, I would like to say, a visionary in terms of bringing open source chip design to at scale and to help democratize this for the larger community. And we hope that at the end of each presentation, feel free to ask questions, and if anything, I want to make this more also as an interactive discussion, suggestion. Right. So with that, I will get started. So I am part of OpenROAD, as well as I had customer success and outreach programs for OpenROAD through Precision Innovations. And I'll talk a little bit about what Precision Innovations also is doing with respect to OpenROAD. So with that, let's get started. So OpenROAD stands for Open Realization of Open Accessible Design. That's what the road is about. And it's a US government DARPA initiative as part of the Electronics Resurgence Initiative. And OpenROAD, the mission is to democratize IC design. And that's a pretty tall order. And what that really means is make chip design easier for the larger community of learners, for hardware engineers, software engineers, and anybody who wants to use this. And why this is important as well, I'll talk about, and why this is also something that needs to be done today and now, and there is that component as well. So it is about democratizing IC design, and primarily the goal is to lower costs and boost innovation at scale. And as I mentioned, this was formed in 2018, and we are into the 5th year of the project, and we have achieved some significant milestones, which I'm happy to share. UCSD, University of California, San Diego, is the prime, and we work closely with other universities and industry collaborators. Professor Andrew Kang is the prime investigator, and his team. He has PhD students that develop parts of the program of the software, and then we also work closely. We, as part of Precision Innovations, we are the key developing organization. We develop large parts of the code, and we make the tools ready for the users, which means that is across the board, which is for industrial applications, for EWD, which is education and workforce development programs, and in general make OpenROAD usable. And we also support that. We fix problems, we enhance the tools, and so on. So that's how Precision Innovations come into the fore. And other collaborators include University of Michigan, Minnesota, Arizona State University. We worked very closely with ARM and Qualcomm at the inception of the project. And as I mentioned earlier in my introduction, Google is a major sponsor and a visionary for this project to make this industry ready, and also given their scale and outreach, to bring it to a wider community of users all over the world. And one specific area of focus for them has been to support what you call as open MPW programs or MPW shuttles, multi-project wafer shuttles, whereby uh, anyone, and I literally mean anyone. You don't have to be a very experienced hardware designer to do chips. You could also be a student or a hobbyist, but you can build design chips using the OpenROAD flow, and then submitted for manufacturing in any of our foundry partners, including Sky Water and Global Foundries, and actually get a chip back and test that. So it's quite a remarkable a vision and achievement to be able to take chip design all the way from spec or design to silicon. So that's been their contribution, and they continue to work very closely with us. And I'm sure Ethan is going to talk more about that. So why are we doing OpenROAD? Why is this important, especially today? The primary reason is costs. Chip design is a very expensive process. It can take millions and millions of dollars depending on the kind of application you're building. And these costs have mounted over almost 19x since the past 2 decades. And if you see the chart on the right, you'll see that what you see on the x-axis are what we call as technology nodes, and these are basically processes from where these are called nodes because they have very specific requirements in terms of the actual feature sizes in which the chips are designed, very specific rules and technologies in which they are designed. And as they advance, you see from 65 nanometer all the way below 10 nanometer, the costs have gone up, 19x. And one thing is cost, the other thing is accessibility. These tools are not easy to access. There are 3 or 4 major EDA vendors. EDA stands for electronic design automation. These companies like Cadence and Synopsys, for example, they make the software to build these chips, right? So EDA is the electronics design automation software that is typically used to build these designs. And they cost a lot. They are extremely expensive. They are not easy to use, and hence, and also not accessible for the larger community. And they also tend to focus very heavily on the leading nodes, which is what's happening today, and not great support for the more mature nodes over the past 2 decades. And these are still very viable nodes, and I'll explain to you why that is important. So the ability to support the whole spectrum of applications across these processes is critical. And furthermore, I do want to point out that it's also the being able to take advantage of computational efficiencies that have occurred over time. So the whole availability of very high performance GPUs and processors that have been possible over the last couple of decades for sure is something that current tools don't take advantage of fully. As you can see on the pink circle, even though we have achieved great results in being able to put increasingly higher functionality and transistor density on chips, as you can see from these curves on the right, what you see is the processor or computational efficiency pretty much remains flat. And these are inherently due to the architectural limitations of today's tools. They are just not built to take advantage. And being able to retrofit that and take full advantage of the cloud and just fast processors and servers is not something that is given a very high priority. So that's the other reason where open source tools come into the picture, and they are able to do that off the bat. So that is the other advantage. So in summary, why are we doing this? We want to remove the barriers to cost of using these tools, cost of chip design, the access for anyone who would like to use these tools and build chips. Any expertise barriers, you don't have to be an expert. You can be anyone. I mean, you can also be, we've had high school students do this. And you can actually learn chip design, which used to be a very esoteric field up until a few years ago. And then finally, to overcome the risk of not being able to deliver your products, on time to market. So these are the barriers that OpenROAD seeks to eliminate. And very specifically, our mission is to do the complete flow that we say from RTL to GDS2, which is essentially means from the specification to all the way to GDS, which is a layout ready format for manufacturability in less than 24 hours, which is a very specific mission we have. And today, this can take running these flows can be days and weeks. And so having this particular goal, which is being able to run these tools, in an autonomous manner, that's the other thing, which is no human in loop, which is, all these, there are so many specific stages, and I'll share that, to be able to run that in an autonomous manner within 24 hours using permissive and open source licensing, right? This is our mission. This is what we do. And finally, we consider OpenROAD is actually a foundation application. And innovation, I want to stress on that. Why innovation? Because if you don't have access to tools that run, that are not hampered by licensing costs, that are able to run on, resources, hardware resources openly and rapidly, hardware engineers can actually take advantage of this and run their experiments and show and be able to try out multiple designs before they come up with something that works really well. That typically these parameters tend to be what's the area of my chip, what's the frequency, the performance, and most importantly in today's era of AI oriented applications, what's the energy efficiency or power consumption. And today, innovation is hampered, as I mentioned, because of just the barriers to access and the time to market constraint and the costs of running so many experiments to be able to innovate and research. And OpenROAD enables that. And we'll talk a little bit more about that in detail. I do also want to mention that we are a key resource for education, training, and workforce development, which is another very critical need today in the industry. And let's see why is that. So this is just a very quick overview of how chip design is done today. I won't go into big details, but essentially it is you start with gathering specifications of your application or your ASIC that you're trying to build, which is an application specific IC. And then you move to do what's called RTL design, the logic design. And this is the stage where you need to get your architecture of how your chip is going to behave and the goals right. And this stage determines how good and what the results are going to be, right, in terms of area and performance. So this is a very critical stage. Functional verification to make sure that the stages, your logical hierarchy delivers the right, behaves functionally correct to the spec. And the next stage is synthesis, which is where the RTL, which is typically written in Verilog, another hardware description language, is synthesized into a circuit description called the netlist. And it's at the gate level, which is where and beyond which you do what's called physical implementation, which is really laying out this netlist on a chip. And that includes details of floor planning, placement, routing, including timing analysis and optimization at various steps in the flow. Finally, signing it off before you with a full chip verification for timing and performance and other key design parameters before it is taped out into the foundry. And although this has been represented as a straight arrows leading into the next block, these are typically iterative processes. There are a lot of today the way it happens is there's the front end architectural or logic designer. These are individual folks, each are having expertise in their own area, and they work very closely to produce a design that can be then synthesized and laid out. And the physical design team is yet another team of experts that work together in laying this out physically as it will appear on the chip. The verification is a parallel design flow stage, which is again run by a set of different team experts that ensure that this design performs to functionality, to timing, it is correct for the design rules set out by the fab, and so on. So if you see this, so you can today the way it's done is it's done using the EDA tools, which teams of experts that focus on very specific stages of the design. There are thousands of commands literally, and it is fairly complex, and it's an iterative process. And this often, poses risk to the in terms of project schedules, and that basically limits the ability of design teams to focus on how, productivity. How can we do this in a manner that is faster, less costlier, and meet the design turnaround time? So that does not get the necessary attention usually. So what OpenROAD does is, that's where the no human in loop and autonomous flow comes. Having said that, we don't trivialize the fact that this is something that can be done from the first stage of the flow to the end before you tape out without requiring any intervention. That's not the case, but largely we do this no human in loop paradigm. But we do allow users to intervene at various stages, analyze results, and look at that. So this is the no human in loop, and automation is a significant paradigm change. I want to talk a little bit about why, again, we are doing open source design, and kind of zoom out a little bit with the looking at the landscape of the semiconductor market. So what you see on the right is a chart by McKinsey, and you can see that in 2021 it's a close to 600 billion market, $600 billion market across all of these applications areas, and that is projected to double to almost 1.1 trillion by 2030. Right, this is the projected growth across these. And as many of you may be aware, today there is a huge explosion in AI related applications, and this increasing the need for a very high performance, energy efficient AI based accelerators is further expanding, this big chunk here that you see. So the need is being driven by the market today, and various governments and including the U.S. government has recognized this, and they've passed the CHIPS Act last year, which allocates more than close to $300 billion across design and manufacturing for the industry, and various education and workforce development initiatives. Right, we'll look at some of these numbers. Now, this, we cannot reach these goals with business as usual, with the traditional pathways into the industry of learning VLSI designs, which today requires, advanced master's and PhD courses, and excuse me, and getting to a trained workforce, that is productive to deliver to the needs of the industry. So this is really the time why we need open source innovation in chip design, which is going to, open the funnel for, the potential talent pool, users, and learners in order to meet these goals and sustain that long term. So that's why this is so critical at this point in time. So essentially, we aim to be like the Linux of the EDA world, or the chip design world. And so democratization, this is not just for the industry, but for research to spur innovation that is needed. This is particularly important for the US, which is reclaiming its leadership back in design and manufacturing, and is a major impetus that's being given to that as it's happening today. We have seen several funding opportunities and funding that's already being allocated to various semiconductor hubs around the country. So this is very critical for national geopolitical and the industry needs for semiconductors. Finally, I do want to also mention that, excuse me, that this is interestingly also very important to spur innovation in semiconductor startups in the US, which today most of the funding is going to AI related applications, and in the computers engineering discipline. So we need to get more people back into design. Excuse me for a second. Startups, excuse me. Startups cannot afford the high licensing costs, and that will basically tamp down on their ability to innovate in the global marketplace. So we have seen, interestingly, several semiconductor startups beginning to use OpenROAD, which is a huge paradigm shift because they typically, again, these tend to be very proprietary in terms of the tools that they use. And so this is, and I'll talk a little bit more about, why that's happening and how that's happening. So this is the overall picture of why we are doing open source chip design and why it's relevant in today's time. So now on to the main flow. OpenROAD is, as I mentioned, it's a low cost and easy to use. That's the area of focus. And we go from, it automates the entire flow from spec to layout. And these are, well-known chip design stages, from synthesis, flow planning, placement, clock tree synthesis, optimization, the routing of the signals on the chip, as well, and finally layout finishing, which ensures that the design is ready to be manufactured and it satisfies all the design rules as laid by the foundries and meets the functional requirements. And the inputs are Verilog, which is the hardware description language for the design, along with other libraries that are used to build, or the building blocks for this design, as well as constraints, which actually specify, very specifically what kind of design constraints that this must satisfy. And I won't go into a lot of technical details, but I'm happy to answer questions as we kind of progress this, because I wanted to give a very high level overview. So, but if you have questions, I can address them at the end of the session. So I already covered the flow here. It's less than 24 hours, no human in loop. And it's manufacturable. So this is not just pure research. We have proven tape outs through the MPW shuttles, and we have internal tape-ins, and these are all from 180 nanometer down to 12 nanometers. So our goal is that we continuously also test and support the latest technology nodes, and we have a suite of designs that we test internally. Vitor will go into the details of how we do that. And these are both commercial and proxy PDKs. PDK stands for physical design kits. So these are building blocks essentially of cells or components for the design that designers can use to build their design. And these include both public, it has open source PDKs, which are again very critical for anyone to be able to do open source design, as well as private PDKs. So we support that, and these are under NDA, and Vitor will cover that in detail as well. And having said that, there is a significant paradigm shift in how OpenROAD builds out this flow. We definitely complement commercial EDA tools because they do a very good job in delivering to the latest nodes, and they have a very strong installed base. So we are interoperable with them, and we also have support sign-off quality flows. And since OpenROAD is a foundational application, anyone can build a flow on top of OpenROAD application and for their own purpose for chip design. And we have several other partners in the ecosystem who have done that. OpenLane from eFabless is a very prime example. And they run a very successful MPW and Chip Ignite program that allows you to build out these chips for a very nominal cost, $10,000 or so. And they run these shuttles, and these are sponsored by Google as well. There have been 8 shuttles so far. So this allows you to basically take an open source build design all the way to layout. And now, typically people tend to focus on the leading and bleeding edge, which is today anywhere below 12 nanometers. But there is a huge market also, which is very viable for applications that sit in what we call as a big fat middle, which is 180 nanometer all the way down to say 28 nanometers. And these applications are very, very relevant today. They are built out on the RISC-V based typically processors, and RISC-V is also a very becoming increasingly popular way, as an open source, OpenISA instruction set architecture, processor, which is the basis for several applications in that domain. This includes IoT, battery operated, fitness wearables, smoke alarms, and so on. And so these OpenROAD is actually the perfect tool for this because it's easy to use, fast, and doesn't need the complexity of today's advanced EDA tools. And so we are increasingly seeing users build out their applications using OpenROAD for these applications today. And primarily the advantages they have is to be able to build this out, at a low cost, as well as, the business case, which is the ability to build these applications or these products in, volume as needed, high volumes, but with a very stringent time to market requirement, which cannot be fulfilled by ASICs designs in the nodes below 12 nanometers. They usually take hundreds of millions of dollars to design in terms of engineering cost and effort, all the way to manufacturing. So we see OpenROAD fit very well, ideally, in this big fat process in a technology spectrum. I'll just talk a little bit of how OpenROAD is useful for innovation. As I mentioned in today, the architectural stage or the early design stage is where there is maximum leverage and opportunity to optimize for power, and most like 30 to 50% of power trade-offs and decisions are made in the early design stage, and the ability to do that without any being blocked by access to licenses or the number of licenses you can run, or the way you distribute your processes across over the cloud or your servers in an unhindered manner is what is needed for systems architect and RTL designers to innovate. And that's what OpenROAD does. And this is very specific. We have customers today, for instance, like Asenium, they make the next generation processors, general processors that are very energy efficient. It's a startup. And they use OpenROAD to do what's called microarchitecture explorations early in the design stage. And they're able to build out prototypes, system level prototypes for early testing. And then eventually when they build the product out, they can go into using commercial tools. And as I mentioned, the early design exploration is where one has the maximum advantage to make trade-offs in between hardware and software and various design goals. And as you progress further into the design flow, as I showed earlier, past physical design, it becomes increasingly different. The levers are fewer to be able to, make radical changes, for your design parameters. And it is also far more expensive to keep iterating in the back end. And and this is just a picture on the right to show how we do early using RTL hierarchical exploration. You can build out very specific hierarchies that have been proven with physical design implementation very rapidly using OpenROAD, and this enables the RTL designers to build out very good logical hierarchies in their Verilog. OpenROAD also uses machine learning and leverages the cloud for computational efficiency. And we have a tool that called the Auto Tuner, which allows designers to rapidly run setup experiments and runs hundreds and hundreds of experiments concurrently. And then using machine learning, it breaks down the design space into what is viable and and specifically delivers the results that meets the best outcomes. And these outcomes can be anywhere from performance, clock periods, or wire lengths, which is just the lengths of the long wires, all of which are key components of timing and performance of the chip. So the ability to do this very rapidly and at no cost is significant for innovation. And OpenROAD will continue to use ML-based technologies moving forward to do a better job at cost at results or PPA estimation, and to bring efficiencies of computation over the cloud. This is an example of an advanced design in GF12. It's an AI chip that's been at GF in the 55 nanometer global foundry node, done internally and excuse me. And this is one of the examples where we ensure that this technology is viable for the current process nodes. And Army Research Labs is, as since we are funded by the DARPA, they continuously test and use our tools to ensure that they work with today's design requirements. And on the right is another example. University of Michigan is a strong collaborator, and they have created this analog chip, which they integrated using the Open Titan framework with OpenROAD. And this is another example of our collaboration of how we work with our ecosystem partners in the open source community, to expand the scope of chip design in applications. How are we doing with time? Just wanted to check. I have another.
It's a little after you've been talking about. You're at 34 minutes. I don't know how long your presentation was.
Okay, I want to cover about I don't know, 10 minutes or so, because I want to cover education and workforce development, which is very key. And then I will hand it over for Q&A. So this is something that we are very passionate about. I do want to again point to share why this is important. The picture here shows that there is the requirement for the industry is about 114,000 jobs by 2030. And this is something that the US government has very strongly is driving and enforcing through the CHIPS Act. And if even with business as usual, you're going to see a shortfall of 68,000 or so. 58% of these jobs are not going to be filled by 2030. And hence, OpenROAD is very significant to be a key solution for training, and thousands in the workforce, both through the educational institutions. And I'll talk a little bit about those programs, and to ensure that we also provide programs to upskill, to meet the requirements of the industry within this time frame. And as the map on the right shows, the various areas in the US where these initiatives are unfolding. And one of the key thing is to, for anyone to adopt and, learn a new area, right? You have to make it fun and build enthusiasm. And chip design until this point has not been that. It's tend to be very siloed and esoteric. And our goal is to, do that. And we see organic engagement in our community of, you don't have to have a EE degree, you have computer science, some background, and you can jump straight ahead and start playing with the tools and even attempt to build out a chip, right? So that is a very key component in kind of bringing these tools to the masses and start earlier in the educational path. So we have UCHC extension courses using OpenROAD along with the other EDA tools that is being offered to the professionals in the Silicon Valley for upskilling. OpenRAM is another project, out of UCSC by Professor Matt Goodhouse, and he, generates compiled RAMs, and this is also something that is supported as part of the OpenROAD flow. And another example of collaboration to add, specific functionality for the chip design flow all through open source. And we have seen a spurt in summer internships programs that have organically been created across various universities in the US and abroad. And here are some examples here on the right: Carnegie Mellon, MIT, and of course our GSOC programs that we have done over the last 2 years in offering OpenROAD projects that have been quite interesting, I hope, and I hope we can grow that out further. I do also want to mention that OpenROAD is actually a fundamental enabler for businesses, that commercial businesses in the education and workforce development programs. Matt Venn conducts a very successful program called, like Tiny Tapeout, whereby you could build out very small chips and literally for like $100 you can get a wafer back and along with the PCB and test it out. And this is a very popular pathway that we see for learners, even including high school courses and undergrad courses, that can, whereby students can do chip design and have their designs taped out, and actually test them out. So these are some exciting times in how education in this area is unfolding and expanding to meet the needs of the industry. We have workforce development programs as well as faculty development programs. And here, this is another example in India, which combines the RISC-V based product development, again using RISC-V and open source tools. And we are also kind of now advancing into the LLMs, generation, where you can build these designs out, starting from LLM, just a prompt, and then there's some, those are the use of generative AI in chip design is almost inevitable, and we are seeing that also come into play. It's an example of a faculty development program that was run earlier this year in July in India, and was very successful. We conducted this in conjunction with our industry partner in IBM. And the focus was to be able to build low power cores such as microwatt, hands-on projects and tutorials, and also train faculty and students to build this out using open source tools that are popular in the industry. I think I talked about most of this, about the industry that's spurred by high processor computing, Gen AI, data center applications, and how OpenROAD sits very closely in that ecosystem, including fabless semiconductors. There's a testimony of one of the users from founders of a Silicon Valley-based semiconductor startup who are definitely including OpenROAD as part of their product development methodology, because it's almost inevitable for them. They are unable to innovate due to costs, of the licensing tools. So we are happy to see that. Our community is growing, and we try and support that across various forums, including LinkedIn, Slack channels where we have very active discussions, and GitHub forums. I think I'll let Vitor talk about that. Our website has a lot of resources that learners can access. This includes, tutorials, documentation, links, blogs, and so on. And here are some links, and you should be able to refer to these to find some more additional resources on the project. And I do want to also mention that we have recently launched the OpenROAD initiative, which further expands the vision that OpenROAD has built out for democratization of chip design. But we want to be able to work and support our other open source industry partners and sponsor projects in chip design, EDA, that together lower cost and democratize access to tools, provide training and innovation for the industry. So we will continue to work through this initiative and reach out the larger community. And here's a quick summary of our projects at GSOC. Our goal has been to make OpenROAD easy to use and learn, right? So a very simple goal, but it is critical because it really makes it the ramp up time to be productive in this tool, significantly lowers that. And we do that by simplifying installation, providing tutorials, documentation. And these are the projects that we have offered through GSOC. And in 2022, we had our intern Arman, who built a tutorial showcasing a hierarchical flow. And this is interesting because, building out a design hierarchically is a very important way to address large designs that cannot be done flat, that have to be done hierarchically using building blocks. So we added that. And in 2023, I think you'll hear later today from Jack. He has done an excellent job of, we've worked together in revamping and overhauling our documentation infrastructure to modernize, use some of the latest tools and techniques in documentation, provide standards across all the tools that are part of the flow, and ensure that information is complete. We are also currently working on a chatbot to help our community, just get basic answers to popular questions that are, often found in GitHub or Slack. And there is a LLM model for EDA that was announced, and this is a very interesting development. And OpenROAD is, is part of that mentioned in the paper, but we do have a goal to also provide this integration moving on to make EDA and chip design even more easier to use. Okay, I think that's the end of my talk. Thank you so much for your time and your attention. And I definitely, again, want to reiterate my thanks to Stephanie and Carlos and the entire UCSC program office for this opportunity.
Great. And you had wanted to do Q&A right after each presentation, you said, right?
Yes, relevant to,
Yeah.
And then I guess I will hand over to Vitor.
Okay, great. Well, Carlos has a question.
Yeah, thank you, Indira. This was a great talk. Really enjoyed it. So I have a very quick question because that came up yesterday. Do you guys have any relationship to NumFocus? I'm just mentioning this because that's another organization that has a vast Python portfolio, and there is some estimate that it actually covers a majority of all scientific software that's being used in a research university. So I was wondering whether you have any kind of relationship with NumFocus. I'm mentioning this because there are some opportunities there to both in a sense of looking at dependencies. They're having contractors who look at supply chain security, and there might be actually ways of leveraging that also within the OpenROAD project, but also a lot of the software that is managed by NumFocus is essentially a cloud stack and that is sometimes run on-premise clouds, right, or science clouds, right, and sometimes on commercial clouds. But on the science cloud side, people are very interested in using accelerators and all kinds of new hardware that I think are sort of in the scope of what you guys are looking at. So I think there could be like multiple touch points with NumFocus, and I'm just curious whether you have thoughts on that.
No,
Thanks.
actually not. Thank you for the link, and thank you for this, the perspective. No, we haven't, but we'll definitely take a look. But I want to also, maybe Ethan or Vitor have something to talk about that, or, all right. No, actually we don't, but thank you for the pointer. Yeah, we'll look at that.
Yeah, we can make introductions if you need them.
Okay.
So we have a very good contacts with them. So yeah, we can do this offline.
That sounds great. Yeah, thank you. Any other questions? Okay, I guess I'm sorry, I think I kind of overran my time, but I tried to, I wasn't sure if the attendees today were familiar, so I kind of wanted to go a little slow and elaborate. So thank you, and I apologize if I've kind of overrun on my time. But if there are no further questions at this point, I would like to have Vitor take over his session next. Thank you again.
Thanks.
Hi, everyone. Thank you, Indira, for the presentation of the project. My talk is a little bit more technical about the open source development of EDA tools. I'm going to focus a little bit on the challenges of testing and evaluation of the EDA tools and things that we have to work with on our everyday as developers. So a little bit of context, EDA tools have a heavy dependency on data. We have many academic papers about algorithms on EDA, but the majority of them don't have real-world data. This is because advanced PDKs, meaning the real-world data, is very restricted. To have access to these PDKs, you have to sign NDAs, and this makes difficult or even prevent publication of results. Right. So the goal of my presentation is try to answer how we can work with private data and still make code contributions public while respecting the NDAs and keeping the data secure. So the basic code development cycle is that you have an idea, you go implement the idea, you test it, evaluate, and then adapt and repeat, right? So for the implementation, you can use any text editor, a simple compiler and debugger should be enough to deploy your code. For test, you can always write your own unit test and regression tests. But where it begins to be tricky with EDA, especially, it's with benchmarks, right? And finally, the evaluation, you can use Python script, generate graphs and tables to analyze the test data. So the problem with EDA is that the data required to run meaningful benchmarks, meaning the PDKs, they are not open source. They are, as I mentioned before, protected by NDAs, and they are very hard to get access to. So what are PDKs and why does it matter? So PDKs are physical design kits. They contain the information required to manufacture a circuit. That is the timing libraries, the physical information of the standard cells, the building blocks that compose a circuit. There are two main types of PDKs. We have commercial type, the commercial and the proxies. Commercial PDKs are used by foundries like Global Foundries, TSMC, and Intel. They, as Indira mentioned, they usually work with the bleeding edge processor nodes. The process to get an NDA to get access is very difficult. The publication and distribution is prevented by the NDA. Up to recently, all the commercial PDKs were private and NDA protected. But thanks to many open source hardware initiative and Google, we now have some PDKs that are open source, albeit in certain older technology nodes like 180, 130, and 90 nanometers. However, in order for our EDA to be competitive and support the newer technology nodes, we still heavily depend on private PDKs. The second type is proxy PDKs. They are usually developed by academics in an attempt to mimic as close as possible the commercial PDKs, but without the restrictions of the private PDKs. Although they are very useful for prototyping, in the end, validation needs to happen with commercial and advanced nodes PDKs. So how to use the proprietary data to drive open source software? The main requirement is that NDAs must be honored. That's the main point. So the PDK data needs to be stored securely. Access to the data must be restricted to authorized personnel only, and the code must not reveal any aspect of the protected data. And as we are talking about open source, all code, the tool code that is, must eventually be made public. So the solution that we found was to create different types of users to control access, as well as having multiple and isolated server clusters to secure the data, and automation for security, integration, and productivity for developers. So Going over the access control, we have three main types of contributors: full, limited, and public access. Contributors with full access are those with access to the private PDKs. They have signed NDAs with foundries. They have access to the secure servers and full access to the private data. We have also limited access contributors. These are trusted developers, and although they don't have access to the PDK data, they still have to sign an NDA with Precision Innovations. And this allows them to trigger benchmark runs, meaning the CI, on the private PDKs. And finally, we have the public access contributors, that is everybody else. Everyone can make contributions based on the public available PDKs that we have. They don't have access to private PDKs, and this type of user cannot trigger the private PDK CI for security reasons. On the server infrastructure, we work with 2 clusters and personal machines due to the nature of everybody being on remote work these days. So the private cluster is self-hosted by us. It's isolated in a network, in a secure network, only accessible for authorized users, those with full access. And they have to sign NDAs to have access to the server and the PDK. We also have a common cluster hosted in G-Cloud, thanks to Google. Users that use this cluster have access to the private code and the public data, but no access to the private PDK data. This is the case for the trusted limited access users. And everybody can download the public data and the public code in their personal machines. To allow this separation of private and public code, we have 3 GitHub organizations. So the first one is the public, is the main one, the public facing. Anyone can create a pull request and contribute. So this follows the normal open source workflow. This holds the reference copy of the code base. So whenever we reference the code, this is the one that we use. No one can directly commit or add branches to the repositories in these organizations. We only accept contributions via pull requests. And since project management is critical, all issues, discussions, and the pull request reviews happen in the public organization for transparency. Our private organization is limited for trusted developers and full access users. They can add commits and branches. Every time that somebody adds code to any repository in this organization, we run a series of security checks to make sure that there are no data leaks of PDK data or private information. And after the security checks are done, and when we are ready, when the developer is ready, they can create a pull request and start an automated workflow. I have a demo later on about the workflow. And finally, the third organization that we have is a staging one. The main reason for this organization is to keep the contributions only via pull request rule. So instead of committing things directly to public, the workflow, the code goes from private to staging and staging to public. So in summary, the the main problem is that only a few users have access to the private PDKs. So how can developers without access to private PDKs be productive? And how to make sure that data is not leaked by accident? And the answer that we found was with automation and CI/CD tools like Jenkins and GitHub Actions. And here I have a short video demo. If anyone has any questions during the demo, please feel free to stop me and ask your questions. So in this demo, let's say I'm just making a quick change. What could go wrong? I think everybody here once in their lives try to do something like this. They just have a quick change commit. They add everything in the path, and they try to make a commit. So here this is the first line of defense that we have to avoid leaking any data. We created pre-commit Git hooks. This runs a security script that checks all the data that is being added to the commit before creating the actual commit to make sure that we are not leaking any sensitive data. So here, for example, you can see that the security check fails and the commit is not completed. So that's not good. Let's start over and do things right. So if we take a look at the simple file that was added by mistake, the file would have contained protected information about Jeff12, a private PDK. So instead, here I'm just going over and adding the actual files that I should have added to begin with. And here you can see that for the tools OpenROAD, the security check was skipped because tools OpenROAD is actually a submodule, and this submodule has its own security checks. So for a code to exist in this submodule, the code must already have passed the security checks. And for the code that I'm adding in the second command here, the JSON files, the security check ran and it passed it. So here I'm just adding some information about the commit message. And then we can go ahead and push the code to the private organization and start the process. I tend to first do a git push with the -n. The -n just does a dry run, just so I can make sure that I'm pushing to the correct place. And then I can use this link provided by GitHub to create the pull request. Here's just some formatting to make sure that the pull request has all the information. And here you can see that these scan codes that are running, these are another security checks that we do before beginning the sync to the public side. So after the security checks are completed and they pass, we can add this custom GitHub label, ready to sync to public. When we do that, this triggers another action and a bot removes the label. And then, as you can see here, the branch has not been deployed yet, meaning the branch is not available to the public. After the action finishes, the bot deploys the pull request to the public side. And here you can see the click on the view deployment to see the public side. So now you can see we are on the public organization, right? The commit came from the staging area. So we are not breaking the rule of only adding code contributions via pull requests. All the information from the pull request has been copied over, including the description. And here you can see the regular CI using the public PDKs are running. And here we go through the normal review process of a pull request, where we request a review. In this case, just for an example, I'm requesting a review for myself. We go over, we make sure that the change is good, and approve it. So one of the features that we have also is to do metrics analysis. The first thing that we can do is to look at all the designs. So each of these pairs of green dots, green check marks are actual designs that we are running through the complete RTL to GDS2 flow. So as you can see, we have a lot of designs, all of them run in parallel and in separate machines. And even with that, each CI run takes over 2 hours. And here, if a design fails, we can take a look at the logs. Another feature that we have available is the OpenROAD dashboard. This is a website that's publicly available. We can select here, for example, to compare a pull request and to analyze the data. Here we have historical data from the master branch, and here we are selecting the pull request that we just started. Here we have an overview of the improvements and degradations for all the public platforms, public PDKs that we support. This tool can be used by developers to identify if a pull request is worth merging or not. For example, when we add a new feature, we might want to, it's hard to add a new feature where for every design and every platform, there will be only improvements. So here the developers can use this tool to filter out, for example, here we are filtering only the degradations for this specific design. And then the developer will be able to have more data to make a decision if the pull request should be merged or not. We also have predefined filters for the most important metrics. And we can also filter by different stages of the flow, like global route or power only related metrics. And one last thing that I want to show is the metrics trend dashboard. Here we are seeing for one platform and 2 designs, the metrics trend over time. So here I'm only showing the last couple of months, but we have more data available as well. And here we can see how the tool is behaving over time. We can identify points where things get a lot better or worse and investigate the reasons when needed. And I think that's it for my presentation. Does anyone have any questions, comments? Well, if anyone doesn't have any questions, I think I'm going to pass over to Ethan.
Great, thanks.
Yeah, sorry, I'll try to go quick. I know we're probably a little over time. But
Yeah,
hey,
for timing, our next session doesn't start till 11:10. It'd be good to have a 10-minute break. So if we go over a little bit, to 11, it should be okay.
Okay, I mean, it shouldn't be that long. So
Okay, cool.
yeah, so hey, I'm Ethan. I'm a software engineer at Google. I actually don't come from the chip industry or the hardware industry. I'm more of a distributed systems person by trade. So I used to build a lot of file systems at IBM, and at Google I did a bunch of like distributed testing things, but always had a little bit of an itch for hardware and trying to understand, how the modern hardware we build our software on works. So a couple of years ago, I joined a team that was trying to, increase the number of people in hardware so that Google can benefit. And I'll talk about a little bit more why Google is starting to do a little bit more hardware. So I would say our story kind of starts, or Google's story starts kind of with exponential curves. So at the end of the day, Google makes money and makes products that help people. So we make YouTube, we make search. These are like huge products that grow exponentially to this day. And one of the things we've noticed in the last couple of years is that the CPUs are not really exponentially growing anymore, right? Like they're kind of hitting that plateau of diminishing returns. And, the number of YouTube videos uploaded is not. So it is actually becoming more expensive to host YouTube today than it was like 10 years ago, just from a hardware perspective. So that kind of drives us to look for different solutions that don't just require us buying, more CPUs, more data centers, more power. And so one of the things we decided to do is like try to close that gap with custom hardware. So, today, like Google has custom SSDs, custom storage, custom neural network accelerators, custom encryption. Surprisingly, in our NICs, calling back to that YouTube example, we built our own video encoding and decoding applications that have like dramatically reduced the amount of compute cycles in our data centers. And there's some like medical applications as well, like using these for data analysis. And I mean, I think, pretty clear today with the hype around AI, like the TPU investment that Google made to kind of speed up AI inferencing and AI training has really paid off. And, these really kind of custom applications that can be built can be huge increases in productivity for like the people developing them, as well as the people end users like consuming them. Because otherwise it wouldn't be feasible to kind of do a lot of the things and products Google wants to make. But, the reality is hardware is not easy at all. As like time has gone on, it's become more and more difficult to match the expected performance of the manufacturing process against the actual realized performance of the product you're building. And it takes a lot more people today, a lot more verification. Kind of one thing I always think about as a software person is, how often is it that you write your code from scratch, beginning to end, and then you compile it, run it, and it works the first time? That's kind of the reality that hardware people live in. If you manufacture your chip with a bug in it, well, there's no fixing it. It's kind of like you either live with it, work around it, or you pay a huge amount of money to respin, and a huge amount of time, I think, is the bigger difference. Like it can take up to 4 months from like you submitting something to a foundry to actually getting the chip back. So you can imagine like if someone slips their schedule and they need to respin, like they could lose all their market advantage. So there's a huge amount of pressure on verification and people. And the hardware industry kind of solves for this with a lot of people and a lot of hires. But I think it can be a little easier. And one of the reasons Google's investing in these open source hardware tools, it's not necessarily because we want to, fundamentally shift like things to one side or the other, but I think what open source can really do is help expand the funnel of people involved. And one of the things we know is when more people get involved, there's like a huge expanding of knowledge and like shared interest. And Google will benefit from that, I think, in the long term. And that's the investment we're making, which is to say, like, this expanded knowledge, more people involved, understanding things, coming up with new ideas will actually allow hardware to close the gap, to come up with new techniques, to share across the industry, both with people who exist in it, like today, as well as like the new people who will come and be interested in this, who maybe it wasn't as easy or as available before. And you know, like, I think the OpenROAD project's like a super interesting example of actually being able to come up with an idea, test it out, prove it, and then like the industry at large, beyond just open source, can take those techniques, take the knowledge and apply it into products, as well as like maybe even their own software, which I think is a really positive thing. It really expands the research opportunity, as well as just like the curiosity. I think is one of the driving things that got me into software in the first place, is like wanting to make my own game and there being a lot of resources available for me to do that. But if you're interested in hardware, there weren't as many, and there weren't as many opportunities for you. You maybe had to go to a few schools in a few select countries, and I think that is like kind of like, you know, we want a rising tide that lifts all boats at Google. And at the end of the day, like, we think that these investments in open source will yield more silicon across the whole industry with more experience. And at the end of the day, it will help Google build more helpful products. It's kind of like, you know, why we're investing so heavily in this, because we think it's going to be just so important in the next 20 years for products to really merge hardware and software to kind of come up with the next technological revolution. And personally, like, you know, I think there's a lot of opportunities in like medicine, and, you know, if more people had these skills, like, we could actually solve a lot of problems that seem almost impossible today. Yeah, that's it.
Yeah. Thank you, Ethan. I think if there are questions for any of us, this is probably a good time.
Oh, Carlos has his hand up.
Yeah.
Hi, Ethan. So this is really fascinating. I would love to talk with you a little bit more. We have one of the incubator projects that we have here at UC Santa Cruz is called Skyhook Data Management, and it is about creating a ecosystem around this notion of a computational I/O stack. And since you have a background in storage, I was particularly fascinated because it's all about, you know, how do you extend, you know, existing frameworks, data management frameworks, or even like serverless, you know, serverless frameworks into the network and storage layer.
Yeah, I totally agree with you. So like, I've actually talked to a bunch of people at Google about, like, you know, getting computational elements into NVMe and like seeing what you can do there, because I think there's a lot you can do. Like, I can imagine, like, you can imagine building a database where, you know, your selects or your where clauses are done on the SSD itself. Like, that's like, it would be feasible to do that. I think the question is like really like the programming model is super hard.
Exactly.
And then the other thing is like, there's a question of like latency and like how much it would cost to integrate that compute into the SSD or the controller, and like whether or not that makes sense for like what the controller wants to do, or like if it's better to like disaggregate that into compute. So like, I think that like there's definitely a lot of trade-offs there, but it is a super interesting area. I did like, I threw up a few proposals at Google about like, you know, maybe some like little entrance into it, but I'm not that important. So
so if you are interested in that, we have actually a session on this very topic at 1 o'clock today. Same channel. It's called Creating the Skyhook DM Ecosystem for the Computational I/O Stack. And this is essentially, you know, we're trying to bring together people from various institutions who are interested in this. We have Sandia National Labs, we have Los Alamos National Labs, we have Argonne National Labs, we had also Seagate, and so there's like numerous people who are interested in the space. And what we are actually interested in is not so much at the hardware level. We just sort of take what's there, right? But how can you actually make the hardware more accessible via the software stack without changing all the applications, right? Or without having the applications kind of know about how to properly use that hardware. And so we're experimenting with things like opportunistic offloading, right? Where you basically have enough information in the IO stream that the hardware can basically decide whether to take some of that data reduction tasks or just push back on that, right? And so there's sort of like these new ideas because embedded systems are they don't have many resources, and sometimes you can. So the key thing is, I think, to try not to reinvent anything, try to leverage as much as possible from those very powerful frameworks that exist and receive a huge amount of investment and progress very fast, right? And how do you kind of connect the new and accelerating arrival of new hardware pieces with accelerating open source communities, right? And that's, I think, the real challenge is to sort of make that happen with while minimizing the friction that could otherwise happen, right?
Yeah, I mean, it's a super interesting problem. Like, I think, some of the things, I mean, you could go into like a ton of topics. I think like Amber Huffman at Google is probably the right person to talk to if you want to actually like really get Google involved. I can send you contact information if you're interested. But
that would be great. Yeah, if you could make introductions, that would be fantastic. Yeah, so I think that, and as I mentioned earlier, we're working also with NumFocus that have a lot of the analysis stack, but also Apache Arrow. So Apache Arrow is a very close partner in sort of these very efficient ways of table-based data. And, we find that we get a lot of efficiency from making certain assumptions about the data, including table-based assumptions. So,
yeah, I mean, like I said, like I mean, go into this a long time, but like, it does feel like there needs. I mean, some of the things you need to solve, I think, is like, how do you not deadlock your hard drive, like, running some computation on it. And
exactly.
I think like, there's definitely like tons of like VM models where you can give it like reductions or like let it just consume a certain amount of resources, then it like just breaks. But that feedback mechanism is going to be terrible in the kernel. And like I think it's just the programming model is weird. So like, I think there needs to be some like heavy restriction on exactly what it's allowed to do, but I'm not sure what those right primitives are. Yeah.
Right. Okay. Yeah, it would be lovely if you could make introductions and then we can continue the discussion.
Ping me your email on, I guess, Zoom.
Yep.
I'll try to make the intro.
All right.